We don't know what 95% of the universe is made of. We don't know what happens inside a black hole. We don't know what sent an object from another star system accelerating through ours. We don't know what produced the most famous radio signal in history. A signal that arrived once, lasted 72 seconds and was never detected again. And the agency that is supposed to have answers, NASA, doesn't know either. But it knows about all of these things. It has the data. It has the measurements. It has the images. What it doesn't have, what it cannot put in a press release or a congressional budget hearing, is an explanation. This is the story of what NASA cannot explain. The genuine mysteries. The kind that keep physicists staring at the ceiling at 3 in the morning. The kind where the data says something, but no one can tell you what. It begins with a signal. August 15, 1977, 11:16 p.m. Eastern Time. A radio telescope at Ohio State University, the Big Ear, is scanning the constellation Sagittarius. It is listening on the hydrogen line, 1420 megahertz. Every SETI researcher on Earth agrees. Any civilization trying to send a beacon across the galaxy would use this exact frequency. It is the universal channel. A few days later, astronomer Jerry Amon reviews the printout. He has done this hundreds of times. He knows what cosmic background noise looks like. Low numbers, ones and twos, the quiet static of a universe that is not sending messages. And then he sees it, on channel 2, at a frequency suspiciously close to 1420 megahertz, the emission frequency of neutral hydrogen, the most abundant element in the universe, the precise frequency that every SETI researcher had agreed would be the obvious interstellar hailing frequency for any civilization trying to send a beacon. There is a sequence of characters that should not exist. The system uses numbers 1 through 9 for normal signal intensities and letters for anything stronger. The sequence reads 6EQUJ5. This means the signal started at an intensity of 6, rose to E, then Q, then U, then J, representing signal strengths of 14, 26, 30 and 19 on this scale before dropping back to 5. It rose, it peaked, it fell. It traced out exactly the profile you would expect from a fixed radio source drifting through a telescoped stationary beam as the Earth rotates beneath the sky. The signal lasted exactly 72 seconds. The Big Ear's 2 feed horns each observed a given point on the celestial sphere for precisely 72 seconds before the rotation of the Earth moved that point out of view. A signal from deep space would produce exactly this duration, not longer, not shorter. Jerry Amon took his red pen and circled the sequence. In the margin, he wrote a single word, wow. The wow signal was born, and then it was gone. The Big Ear never detected it again. No telescope since has ever detected it again, despite orders of magnitude improvements in sensitivity. Decades of follow-up observations targeting the same patch of sky in the constellation Sagittarius have found nothing but silence. Total, unbroken silence. 49 years of nothing. In 2024, the Arecibo WOW project, led by Abel Méndez at the University of Puerto Rico, reanalyzed every surviving scrap of data from the Ohio SETI program. Their results, published in 2025, revised the signal's properties dramatically. The signal was 4 times stronger than previously estimated, at least 250 Janskys. Its frequency, 1420, 726 megahertz, offset from the hydrogen line by just 320 kilohertz, implying a source moving at significant velocity relative to Earth. Its origin was narrowed to 2 adjacent sky fields in Sagittarius, near the globular cluster M55. And then the team offered their leading hypothesis, a maser, a natural microwave laser. A magnetar flare striking a cold interstellar hydrogen cloud, triggering a sudden brightening at the hydrogen line frequency. The math works, the physics is plausible, the explanation is natural, and it requires a coincidence so improbable, a magnetar flare at exactly the right moment, at exactly the right angle, intersecting exactly the right cloud, producing a signal at exactly the right frequency, at exactly the right time for a modest Ohio telescope to catch it in its 72-second window, that many astronomers privately do not believe it. The WOW signal was detected by a relatively primitive radio telescope in 1977. Since then, our instruments have become orders of magnitude more sensitive. We have the Allen Telescope Array in California, the 500-meter aperture spherical telescope in China, the largest filled aperture radio telescope on Earth, the Square Kilometre Array under construction in Australia and South Africa, CHIME in Canada, scanning the entire northern sky every night. If the WOW signal were a common natural phenomenon, we should have detected dozens, perhaps hundreds, of similar events by now. We have none, not one. The WOW signal remains singular, a one-time event in the entire history of radio astronomy. And that singularity is perhaps the most unsettling thing about it. The WOW signal was born, and then it was gone. Now, here is where the mystery begins to bite. The big ear had two feed horns, one pointing slightly east, one pointing slightly west. The signal appeared in only one horn. If it were a local source of interference, an aircraft, a satellite, a reflection from the ground, a truck driving past with a malfunctioning radio, it would almost certainly have appeared in both horns. It did not. If it were a natural celestial source, a pulsar, a quasar, a burst from a distant galaxy, it should have repeated at least occasionally, at least once, in one of the thousands of hours of follow-up observations conducted over the subsequent decades. It has not once, not in 49 years. You have to sit with that for a moment. 49 years, nearly half a century, the length of an entire scientific career. And in all that time, with all our advances, with radio telescopes that are thousands of times more sensitive than the big ear, with arrays that can scan the entire visible sky every single night, we have never seen anything like the WOW signal again. The silence that followed is almost as profound as the signal itself. It says something about the universe that we do not want to hear, that the most tantalizing hint of cosmic companionship ever recorded may have been a statistical fluke, a 1 in a billion natural coincidence, or something else entirely. Their findings were remarkable. They narrowed the signal's origin to two adjacent fields in the constellation Sagittarius, near the globular cluster M55. They determined the signal was even stronger than previously believed, a peak flux density exceeding 250 Janskis, roughly 4 times higher than earlier estimates. They confirmed the frequency at 1420.726 MHz, slightly offset from the hydrogen line, implying a source moving at significant velocity relative to Earth, consistent with a galactic origin. Because here is the thing about the WOW signal that no one likes to discuss too loudly. The maser hypothesis requires an extraordinary coincidence. A magnetar flare, already rare, had to occur at precisely the right moment, at precisely the right angle, intersecting precisely the right kind of hydrogen cloud, producing a signal at precisely the right frequency, at precisely the right time for a modest radio telescope in Ohio to catch it during its 72-second window. The probability of all these factors aligning is not zero, but it is vanishingly small, so small that some astronomers privately admit they are not satisfied, so small that the WOW signal remains officially unexplained. Now, consider this. The WOW signal was detected by a relatively primitive radio telescope in 1977. The Big Ear was sensitive for its time, but by modern standards it was almost deaf. Since then, our instruments have become orders of magnitude more sensitive. We have the Allen Telescope Array in California dedicated to SETI. We have the 500-meter aperture spherical telescope in China, the largest field-aperture radio telescope on Earth. We have the Square Kilometre Array under construction in Australia and South Africa, which will be sensitive enough to detect an airport radar from tens of light years away. We have CHIME in Canada, scanning the entire northern sky every night. We have arrays of dishes that can detect a cell phone signal from across the galaxy. If the WOW signal were a common natural phenomenon, if maser flares from hydrogen clouds were a routine occurrence, we should have detected dozens of similar events by now, hundreds, thousands. We should have entire catalogues of WOW-like signals, classified and analysed and explained. They were discovered in 2007, 30 years after the WOW signal, by Duncan Lorimer and his graduate student David Narkovich at West Virginia University. They were analysing archival data from the Parkes Radio Telescope in Australia, the same telescope that had given the world the live television broadcast of the Apollo 11 moon landing, when they found something that should not have been there. A single burst of radio energy, lasting only a few milliseconds, but so powerful that it seemed to have originated from billions of light years beyond our galaxy. In the span of a few thousandths of a second, this burst had released more energy than the sun emits in an entire day. At first, astronomers were skeptical. The Parkes telescope had an embarrassing history of detecting strange signals that turned out to be microwave ovens opened too early in the observatory kitchen. But the Lorimer burst was different. Its dispersion measure, a delay between frequencies caused by the burst journey through ionized intergalactic gas, indicated an extragalactic origin. The signal had traveled through far more free electrons than any source within the Milky Way could account for. It had come from deep space, far beyond our galaxy, but the Lorimer burst was different. Its dispersion measure, the degree to which different frequencies in the burst arrived at slightly different times, an effect caused by the burst's journey through the ionized intergalactic medium, indicated an extragalactic origin. The burst had traveled through far more free electrons than any source within the Milky Way could account for. It had come from deep space, far beyond our galaxy. The leading candidates to explain FRBs are magnetars. A magnetar is a neutron star, the collapsed core of a dead massive star, the mass of the Sun compressed into a sphere 20 kilometers across. But a magnetar has a magnetic field a quadrillion times stronger than Earth's, strong enough to tear apart atoms from 1,000 kilometers away, strong enough to distort the quantum vacuum itself. When the crust cracks under immense strain, a starquake, it releases a titanic flare of energy that could, in theory, produce a fast radio burst. This theory received dramatic support in April 2020, when a magnetar in our own galaxy, SGR 1935 plus 2154, located about 30, zeros and light years away in the constellation Vulpecula, emitted a burst that was simultaneously detected as an X-ray flare by the Swift and Fermi space telescopes and as an FRB-like radio pulse by CHIME and the STAR-2 array. The burst was not as powerful as extragalactic FRBs. It was about 1,000 times weaker, but the coincidence of the X-ray and radio emission was the smoking gun. It proved that magnetars can produce FRB-like signals. The case seemed to be closing, but then the exceptions started piling up. FRB 2540209A, precisely localized in January 2025, came from an ancient elliptical galaxy, 11.3 billion years old, that stopped forming stars billions of years ago. No young magnetars, no star-forming regions, just stars. The burst repeated 22 times. FRB 22000120E came from a globular cluster in the galaxy M81, another place with no young stars. And in March 2025, FRB 225316A, the closest FRB ever pinpointed at just 130 million light-years, was traced by the James Webb Space Telescope to a location near, but not inside, a star-forming region. The Webb data revealed individual stars at the site. Young and massive, yes, but the burst came from outside the obvious nursery, as if the source had been kicked from its birthplace, or was never born there at all. The pattern, if there is a pattern, is that there is no pattern. The energy required to produce these bursts is almost impossible to comprehend. In a single millisecond, a fast radio burst can release as much energy as the sun produces in a century, concentrated into a volume no larger than a city. For an instant briefer than the blink of an eye, a single point in a distant galaxy outshines every star in that galaxy combined at radio wavelengths. And then, in March 2025, came an even more extraordinary discovery. FRB 25316A, soon dubbed RBF, the radio burst from a local origin at twilight, was detected in the galaxy NGC 4141, just 130 million light-years from Earth. This is cosmologically next door. It was the closest FRB ever pinpointed with high precision. The CHIME outrigger array triangulated its position to within a fraction of an arcsecond, allowing the James Webb Space Telescope to conduct the deepest ever search for the source of a fast radio burst. What Webb found was both illuminating and confounding. At the precise location of the burst, there was a faint infrared source, designated NAR1, which could be a massive star or a red giant. Neither is a candidate for directly producing a fast radio burst, but an unseen companion, a neutron star, perhaps a magnetar, could be siphoning material from the larger star, and the interaction might produce the conditions necessary for a burst. Or NIR1 might be unrelated, a chance alignment on the sky, and the true source might be an isolated magnetar surrounded by young massive stars. Stars that Webb also detected in the vicinity, clustered around the burst location. In January 2025, astronomers announced the discovery of FRB 2240209A, a repeating fast radio burst precisely localized to the edge of an ancient dead galaxy 11.3 billion years old, 2 billion light-years from Earth. This galaxy has not formed new stars in billions of years. It is the last place you would expect to find the young, massive magnetar thought to produce FRBs. And yet, there it was, repeating. And then in March 2025 came FRB 2250316A, soon dubbed RBF Lorite, detected in galaxy NGC 4141, just 130 million light-years away. This was the closest FRB ever pinpointed with high precision. The CHIME outrigger array triangulated its position to within a fraction of an arcsecond, allowing the James Webb Space Telescope to conduct the deepest ever search for an FRB source. Here is what NASA does not say in its press releases about FRBs. We are cataloguing thousands of these events, and we still do not know, with certainty, what causes a single one of them. We have theories and models, but every time we think we have a pattern, FRBs come from young magnetars in star-forming galaxies. The universe throws us a contradiction. An FRB from a dead elliptical galaxy, an FRB from a globular cluster, an FRB that repeats on a schedule no one predicted, an FRB that is brighter than any model can comfortably explain. The universe is trying to tell us something with these bursts. We are not yet fluent enough to understand the language and the possibility, remote, speculative, but not impossible, that at least some of these signals might be artificial has not been ruled out. The scientific community is rightly cautious, but the history of astronomy is also the history of discovering that the universe contains things far stranger than we imagined. Pulsars were once too bizarre to be natural. Now they are textbook astronomy, but radio signals, whether the singular WOW or the prolific FRBs, are only one kind of mystery. There is another, the kind you can see with your own telescopes. The kind that shows up on your doorstep without warning and refuses to leave a forwarding address. October 19, 2017. The Pan-STARRS 1 telescope on Haleakala, Hawaii. Astronomer Robert Werrick is reviewing data, looking for near-Earth asteroids, when he spots an object moving across the field of view. Fast, very fast. He checks its trajectory against the database of known asteroids and comets. Nothing matches. He checks its velocity, 87, 3 kilometers per second relative to the Sun, far too fast to be gravitationally bound to our solar system. Even an object ejected from the farthest reaches of the Oort cloud could not achieve that speed. The object was interstellar. It had come from another star system. It was the first confirmed interstellar object ever detected traversing our solar system. They named it oumuamua, Hawaiian for a messenger from afar arriving first. And from the moment of its discovery, oumuamua refused to behave. Comets, when they approach the Sun, heat up. The volatile ices in their interiors, water ice, carbon dioxide ice, methane ice, sublimate, turning directly from solid to gas. This gas streams away from the nucleus, carrying dust with it, forming a bright, diffuse coma that can be tens of thousands of kilometers across, and a tail that can stretch for millions of kilometers. This is what makes comets visible and beautiful. This is what tells us, unmistakably, that we are looking at a comet. Oumuamua passed within 0.25 astronomical units of the Sun, closer than the orbit of Mercury. At that distance, the solar radiation is intense. Any volatile ice should have sublimated vigorously. There should have been a coma, there should have been a tail. There should have been a visible cloud of gas and dust surrounding the object. The most powerful telescopes on Earth and in space, including the Hubble Space Telescope and the Spitzer Space Telescope, were trained on oumuamua during and after its closest approach. They saw nothing, no coma, no tail, no spectral signature of gas or dust, no outgassing at all. It looked like an asteroid, a dry, rocky body, inert and unchanging. The first thing that became clear was its shape. As oumuamua tumbled through space, rotating end over end with an 8-hour period, its brightness varied by a factor of 10, the largest variation ever observed for any solar system object. This suggested a shape 5 to 10 times longer than it was wide. Some models placed it at 800 meters long and 80 meters wide. A cosmic cigar, or perhaps a pancake, thin and flat and tumbling. Neither shape resembles any asteroid or comet ever observed. The astronomical community erupted. Papers were published at a furious rate. Theories multiplied, each striving to explain the data without invoking anything too exotic. As oumuamua raced away from the Sun, it was not slowing down as much as it should have been. Gravity alone could not account for its trajectory. Something was giving it an extra push, a non-gravitational acceleration. This phenomenon is well known in comets. As they outgas, jets of sublimating material act like small rocket thrusters, nudging the comet's trajectory in ways that pure gravity cannot account for. But Oumuamua showed no evidence of outgassing, no coma, no tail, no spectral lines from gas or dust, just a small, steady acceleration in the anti-solar direction away from the Sun. And we will likely never know for certain. Oumuamua is now far beyond the reach of our telescopes. Racing toward the constellation Pegasus at a velocity of more than 26 kilometers per second. But the broader mystery of Oumuamua is not about this single object. It is about what its existence implies. Oumuamua was the first interstellar object we ever detected. It was discovered by a telescope that had only recently become operational, scanning only a fraction of the sky. If we found one so quickly, there must be millions passing through our solar system at any given moment. We are not an isolated island. We are a busy crossroads through which material from countless other planetary systems constantly streams. The Vera C. Rubin Observatory in Chile is expected to detect several interstellar objects per year. Its 8.4-meter mirror and 2 gigapixel camera, the largest ever built for astronomy, will image the entire visible sky every few nights. When the next Oumuamua appears, we will have spectrographs pointed at it within hours. We may even send a spacecraft to intercept it. The mystery is not closed. It is on pause for comparison. Consider 2I Borisov, the second interstellar object, discovered in 2019 by amateur astronomer Gennady Borisov. Borisov was unambiguous, bright coma, long tail. Cyanogen gas, the same molecule in Comet Halley's spectrum. A perfectly normal comet from another star system. The contrast is itself a mystery. Why were the first two interstellar visitors so fundamentally different? Relative to the Sun, it crossed the orbit of Neptune in 2024. It will cross the Kuiper Belt's outer edge in 2025. By 2038, it will pass the heliopause, the boundary where the Sun's solar wind gives way to the interstellar medium, the edge of the Sun's domain. And then it will be gone, truly gone, swallowed by the void between the stars, never to be seen again by human eyes. The most famous and controversial theory came from Avi Loeb at Harvard. Loeb proposed that Oumuamua might be an artificial light sail, a piece of alien technology propelled by the pressure of solar radiation. If Oumuamua were thin enough, with a large surface area relative to its mass, photon momentum could account for the acceleration. The data, he argued, does not rule out an artificial origin. The suggestion was provocative, widely criticized, but not unscientific. The problem was that Oumuamua was already receding too fast for any definitive test. Other researchers proposed more conventional explanations. A team from Arizona State University suggested Oumuamua was a shard of solid nitrogen ice, a fragment of a Pluto-like exoplanet, chipped off by a cataclysmic impact and flung into interstellar space. Nitrogen ice would sublimate invisibly, producing no detectable gas while providing sufficient rocket effect. The elongated shape could result from progressive flattening, like a bar of soap wearing down to a sliver. The math worked. Another team from UC Berkeley and Cornell proposed that Oumuamua began as a water ice comet, ordinary and unremarkable. During its long journey through interstellar space, it was bombarded by high-energy cosmic rays. The cosmic rays split water molecules into hydrogen and oxygen atoms. The hydrogen became trapped in bubbles within the ice matrix. When the comet approached the Sun and warmed, the ice restructured into a more stable crystalline form, releasing the trapped hydrogen in an invisible fan-shaped molecular spray. enough of a push to explain the acceleration. Another team, from UC Berkeley and Cornell, proposed a different ice-based explanation. Oumuamua began as a water ice comet. During its journey through interstellar space, cosmic rays split water molecules, and hydrogen became trapped in bubbles within the ice. When the comet approached the Sun and warmed, the ice restructured, releasing the hydrogen in an invisible molecular spray, enough push to explain the acceleration. On Earth, 90% of atmospheric methane comes from living organisms. The remaining 10% comes from geology, water reacting with subsurface minerals in a process called serpentinization. But methane is fragile. On Mars, ultraviolet radiation breaks it down within 300 years. If methane is present today, something is producing it. Right now, but while we look outward to the stars, searching for signals and visitors, there is a mystery much closer to home. On a planet we have been studying with orbiters and landers and rovers for decades. A planet that, by every reasonable expectation, should be dead, a frozen desert, its atmosphere thin and cold. And yet, on this planet, something is stirring. In 2012, NASA's Curiosity rover landed in Gale crater, a 154-kilometer-wide impact basin near the Martian equator. Among its suite of scientific instruments was the Tunable Laser Spectrometer, or TLS, part of the Sample Analysis at Mars, or SAM, instrument package. The TLS was designed to measure the composition of the Martian atmosphere with exquisite precision, using a laser tuned to specific wavelengths that methane absorbs. It was, in essence, a methane sniffer. If there was methane on Mars, Curiosity would find it. For the first several months of its mission, the TLS detected essentially nothing. The methane background was close to zero, less than 0.7 parts per billion, at the very limit of the instrument's sensitivity. This was puzzling, given the earlier detections by telescopes and Mars Express, but it was not necessarily contradictory. Methane could be patchy, localized, intermittent. And then, in late 2013, the TLS detected a spike. Methane levels jumped to 7 parts per billion, roughly 10 times the background level. The spike persisted for about 2 months and then faded back to background. The rover had driven nowhere during this period. The spike was temporal, not spatial. Something had released a pulse of methane into the atmosphere of Gale crater, and then the release had stopped. More spikes followed. In June 2019, Curiosity detected a methane surge of 21 parts per billion, the highest concentration ever directly measured on the surface of Mars. This was more than 50 times the background level. The spike appeared overnight and vanished almost as quickly, declining back to the baseline within a few days. Again, the rover had not moved. Again, the spike was a temporal event, a puff of methane appearing and dissipating in the thin Martian air. In 2012, NASA's Curiosity rover landed in Gale crater, carrying among its instruments the Tunable Laser Spectrometer, a methane sniffer. If there was methane on Mars, Curiosity would find it. For the first several months, it detected essentially nothing. The methane background was near zero, and then in late 2013 it detected a spike. Methane levels jumped to 7 parts per billion, 10 times the background. The spike persisted for 2 months and then disappeared, and then, just when the data seemed to be pointing toward a fascinating puzzle, geological or biological, but definitely Martian, a team of researchers in Belgium dropped a bombshell. More spikes followed. In June 2019, Curiosity detected a surge of 21 parts per billion, the highest concentration ever measured on Mars, more than 50 times the background. The spike appeared overnight and vanished within days. But the most intriguing pattern was the seasonality. Over years of monitoring, Curiosity's data revealed that methane levels rise in the Martian summer, when the ground warms, and fall in the winter. The pattern does not look like a diffuse, planet-wide phenomenon. It looks like a local source, responding to temperature, something active, something seasonal. The numbers are worth examining. Curiosity's background methane level is approximately 0.4 parts per billion. The seasonal peaks reach about 0.7. The June 2019 spike hit 21 parts per billion, more than 50 times the background. It appeared overnight. It vanished within days. The rover had not moved. The wind direction during the spike pointed toward the northwest of Gale crater, toward a region of fractured bedrock that could, in theory, release trapped gas. But the Trace Gas Orbiter, circling overhead, measured the same atmosphere from orbit and detected nothing. Its upper limit, 0.05 parts per billion. The surface says yes, the orbit says no. This contradiction has never been resolved. What they found was deeply troubling. The TLS instrument has two main compartments. There is the sample cell, the chamber where Martian air is held for analysis, and there is the foroptics chamber, the compartment where the laser emits its beam before it enters the sample cell. These two chambers are separated by an O-ring seal, which is supposed to prevent gas from leaking between them. But the foroptics chamber, the Belgian team discovered, was heavily contaminated with methane. Heavily. The methane levels in the foroptics chamber were 3 to 4 orders of magnitude, 1,000 to 10,000 times, greater than the levels being reported in the sample cell. The contamination, they found, dated back to before launch. In 2011, while Curiosity was being prepared at Cape Canaveral, terrestrial air from the Florida coast, air containing ambient methane, had leaked into the foroptics chamber. Repeated attempts to evacuate the chamber, both before launch and during the mission, had failed. The methane in the foroptics chamber kept coming back, as if the rover itself harbored some reservoir of the gas. The source of this persistent methane was never identified. It might have been outgassing from materials within the instrument, or a slow leak from some other component, or a chemical reaction producing methane inside the sealed compartment. In early 2025, a group led by Sébastien Viscardy at the Royal Belgian Institute for Space Aeronomy published a reanalysis of Curiosity's raw data. Their paper carried a quiet but devastating title, questioning the reliability of methane detections on Mars by the Curiosity rover. What they found was troubling. The instrument's foroptics chamber, where the laser emits, adjacent to the sample cell, was contaminated with methane at levels 3 to 4 orders of magnitude greater than those reported in the sample cell. The contamination dated back to before launch. In 2011, terrestrial air from Cape Canaveral had leaked into the chamber, and repeated attempts to evacuate it had failed. The methane kept coming back, as if the rover itself harbored a reservoir of the gas, but the story does not end there. Even if all of Curiosity's methane spikes turn out to be instrumental artifacts, even if the rover's most famous discovery is a ghost in the machine, the broader mystery of methane on Mars does not evaporate. The European Space Agency's Trace Gas Orbiter, which arrived at Mars in 2016 and carries sensitive spectrometers designed specifically to measure trace gases in the atmosphere, has been conducting a global survey of methane from orbit. Its results have been puzzling in a different direction. It has detected almost no methane at all. Its upper limit for the global background, is about 0.05 parts per billion, far below Curiosity's ground-level measurements. The Belgian team demonstrated that even a minuscule leak across the O-ring seal, less than 1/1000th of the methane-rich air diffusing into the sample cell, could fully account for all reported methane detections. The seasonal variation they suggested might be an instrumental artifact, the Phoreoptics chamber expanding and contracting with the Martian seasons, altering the leak rate. The paper proposed a simple experiment: analyze the same sample on 2 consecutive nights. If methane is higher on the second night, it is leaking from within the rover. That experiment has not been performed. The question remains open, and Mars Express, the orbiter that first detected methane in 2003, continues to report occasional positive detections from orbit, including a well-known plume over Gale crater in 2013 that coincided temporally and spatially with one of Curiosity's ground-level spikes. If the ground-level spikes are instrumental artifacts, what was Mars Express seeing? The coincidence is either extraordinarily lucky, a chance alignment of an instrumental glitch on the surface with a real but unrelated methane detection from orbit, or it points to something real. But the context matters. The sample came from an ancient lake bed, a place where water once pooled, where the chemistry was benign, where the conditions were, as far as we can tell, habitable. The molecules have survived for nearly 4 billion years, preserved in the Martian rock, waiting, and as John Eiler, a geochemist at Caltech, told reporters, the findings reported in this paper present the best chance we have seen for identifying the remains of life on Mars. Meanwhile, in a separate and perhaps more profound development, Curiosity made a different kind of discovery. In March 2025, in a 3.7 billion-year-old rock sample drilled from an ancient lake bed at Yellowknife Bay, the rover detected long-chain alkanes, decane, undecane, dodecane, the largest organic molecules ever found on Mars. On Earth, these are breakdown products of fatty acids, universal components of cell membranes. They can also be produced by abiotic processes. But the context matters. The sample came from an ancient lake bed, a place that was once warm, wet, and potentially habitable. As John Eiler of Caltech told reporters, the findings reported in this paper present the best chance we have seen for identifying the remains of life on Mars. The best chance. Sitting in a sample tube inside a rover on another planet, and we cannot bring it home, so we wait. We wait with a rover that may be detecting methane that is not really there, or may be detecting methane that is the first hint of alien biology. We wait with organic molecules that may be the decay products of ancient Martian life, or may be the products of lifeless chemistry. We wait with questions that have been open for decades and may remain open for decades more. NASA's Mars Sample Return Mission, the effort to retrieve samples cached by Perseverance and bring them to Earth, has been delayed and redesigned. The earliest a return might occur is the mid-2030s, and even that assumes funding, political will, and technical success across multiple unprecedented mission elements. And so the Martian mystery continues, as it has since the first Viking landers touched down in 1976, carrying experiments designed to detect microbial metabolism. One of those experiments, the labeled release experiment, produced positive results. The Martian soil, when fed radioactive nutrients, released radioactive carbon dioxide, exactly as expected if microbes were metabolizing. But another experiment found no organic molecules in the soil. Without organics, the positive result was dismissed as a false positive, probably caused by reactive perchlorates in the soil. The lead scientist, Gilbert Levin, went to his grave in 2021 believing he had discovered life on Mars. The scientific consensus remains that he did not, but the door is still open, just a crack, wide enough for wonder to seep through from the red deserts of Mars. Let us now turn to something even stranger, something that fills the entire universe and yet remains invisible to every instrument we have ever built, something that determines the structure of galaxies and clusters and the cosmic web itself, but refuses to reveal its nature: dark matter. The name itself is an admission of ignorance. The numbers are staggering. Dark matter constitutes approximately 27% of the total mass energy of the universe. Ordinary matter, the stuff of stars, planets, people, everything we have ever seen or touched, accounts for less than 5%. The remaining 68% is dark energy, a force driving the accelerating expansion of the universe about which we know even less. We are, in the most literal sense, a rounding error. The universe is made almost entirely of things we do not understand, and we call ourselves astronomers. We call it dark, not because it is dark in color, it is no color at all, but because it does not interact with light, it does not emit light, it does not absorb light, it does not reflect light. It is transparent, invisible, undetectable by any telescope, no matter how powerful. And yet it is there. We know it is there because we can see what it does. The bullet cluster is the most dramatic evidence. It is not one galaxy cluster but two clusters that collided head-on, 3.8 billion light-years away. The hot gas from both clusters, which makes up most of the visible mass, collided and slowed down, pooling in the center of the collision zone. But gravitational lensing maps, measurements of how the cluster bends light from background galaxies, reveal that most of the mass passed straight through. It did not collide. It did not slow down. It continued unimpeded, separating from the visible gas. This is exactly what you would expect if dark matter consists of particles that do not interact, even with each other. Modified Newtonian dynamics, cannot explain the bullet cluster. Dark matter can. This was the same dark matter that Zwicky had proposed 4 decades earlier, and the evidence has only accumulated since. Gravitational lensing, the bending of light by massive objects, as predicted by general relativity, reveals far more mass in galaxy clusters than can be accounted for by the visible stars and gas. The cosmic microwave background, the faint afterglow of the Big Bang, which permeates all of space, contains tiny temperature fluctuations that encode information about the composition of the early universe. Analysis of these fluctuations by the Planck satellite and its predecessors reveals that dark matter makes up approximately 27% of the total mass energy budget of the universe. The story begins in the 1930s with Swiss astronomer Fritz Zwicky. He was studying the Coma cluster, 1,000 galaxies located 320 million light-years from Earth. The galaxies were moving so fast within the cluster that they should have flown apart. The visible mass, the stars and gas Zwicky could see, was nowhere near enough to provide the gravitational pull needed to hold the cluster together. Zwicky proposed a solution. There must be additional mass, invisible to telescopes. He called it Dunkel Materie, dark matter. The idea was radical, and for decades, largely ignored. For decades. The leading candidate for dark matter has been the WIMP, the weakly interacting massive particle, a hypothetical particle that interacts with ordinary matter only through gravity and the weak nuclear force. It has mass but does not interact with electromagnetism, hence it does not emit, absorb, or reflect light. Billions of WIMPs would pass through your body every second, and you would never feel a thing. On extraordinarily rare occasions, a WIMP might collide with an atomic nucleus, depositing a tiny amount of energy that could, in principle, be detected. In the 1970s, American astronomer Vera Rubin, working with Kent Ford, began measuring the rotation curves of spiral galaxies. According to Newtonian gravity, the orbital velocities of stars should decline at larger distances from the galactic center, just as planets in our solar system orbit slower the farther they are from the Sun. But that is not what Rubin and Ford found. The rotation curves did not decline. They stayed flat. Stars at the edges of galaxies were orbiting just as fast as stars near the center. The visible mass could not account for this. There had to be an invisible halo of mass extending far beyond the visible galaxy. The Large Underground Xenon Experiment, LUX, operated from 2012 to 2016 in the Sanford Underground Research Facility, a mile beneath the Black Hills of South Dakota. It used 370 kilograms of liquid xenon as its target mass. It found nothing. Its successor, lixaplelin or LZ, uses 7 tons of liquid xenon and is 1,000 times more sensitive. As of 2025, after years of data collection, LZ has set the most stringent limits ever on WIMP nucleon interactions. Nothing, no signal, no WIMPs. The Super CDMS experiment in Minnesota uses germanium and silicon detectors cooled to near absolute zero, sensitive to lower mass dark matter particles than the xenon detectors can probe. It too has reported null results. The search for WIMPs has been one of the great experimental sagas of modern physics. Detectors have been built deep underground, in abandoned gold mines in South Dakota, under mountains in Italy, in tunnels beneath the Chinese countryside, to shield them from cosmic rays. They use ultra-pure crystals, liquefied noble gases, and superconducting sensors to watch for the minute recoil of an atomic nucleus struck by an invisible particle. The Lux Zeppelin detector in South Dakota uses 7 tons of liquid xenon and is 1,000 times more sensitive than its predecessor. Xenon Italy, Panda X4T in China, all searching, all setting ever more stringent limits, all finding nothing. This is a remarkable situation. The WIMP hypothesis is elegant, well-motivated, and theoretically compelling. It emerges naturally from extensions of the standard model of particle physics, particularly supersymmetry. It would explain everything: the rotation curves of galaxies, the structure of the cosmic microwave background, the formation of large-scale structure in the early universe. And yet, after decades of searching, with detectors of ever-increasing size and sensitivity, we have found nothing. Not a single confirmed WIMP interaction. Not one. The null results are so consistent and so stringent that some physicists are now talking openly about the possibility that WIMPs do not exist, that dark matter, whatever it is not made of weakly interacting massive particles. And if not WIMPs, then what? The axion is the next leading candidate. An ultralight particle proposed in the 1970s, it would behave more like a wave than a particle, forming vast diffuse halos around galaxies. The axion dark matter experiment at the University of Washington uses powerful magnetic fields to try to convert axions into detectable microwave photons. As of now, no axion has ever been detected. The parameter space is vast, and most of it remains unexplored. Several axion detectors are now operational or under construction. The Axion Dark Matter Experiment, or ADMX, at the University of Washington uses a powerful magnetic field inside a resonant cavity to try to convert axions into detectable microwave photons. The CERN Axion Solar Telescope, or CAST, searches for axions produced in the core of the Sun. The International Axion Observatory, or IXO, is a next-generation experiment that will be orders of magnitude more sensitive. As of now, no axion has ever been detected. But the parameter space for axions, the range of possible masses and coupling strengths, is vast, and most of it remains unexplored. The search continues. The truth is that we do not know. After nearly a century of evidence for dark matter, and decades of experiments searching for it, the most honest answer we can give is that the dominant form of matter in the universe has not been identified. We see its gravitational fingerprints everywhere, in the motions of galaxies, in the bending of light, in the structure of the cosmos itself. But the thing itself, the particle, the field, the phenomenon, remains beyond our grasp. And then there is the most radical possibility, that dark matter does not exist at all, that our theory of gravity is incomplete. This idea, modified Newtonian dynamics or MOND, was proposed by Mordechai Milgrom in 1983. MOND suggests that gravity falls off more slowly than Newton predicted at the extremely low accelerations found at the edges of galaxies, eliminating the need for invisible matter. It predicts flat rotation curves with remarkable precision, but it struggles to explain gravitational lensing in galaxy clusters, and it has difficulty reproducing the detailed structure of the cosmic microwave background, which dark matter models match exquisitely, but they will not tell us what it is. That will require a breakthrough, either a direct detection in one of the underground experiments, or a theoretical revolution that changes our understanding of gravity or particle physics. Until then, we remain in the strange position of knowing, with high confidence, that most of the matter in the universe is something we have never seen. And now we come to the deepest mystery of all, the one that sits not in the sky or on a neighboring planet, but at the intersection of the two greatest theories in physics, general relativity and quantum mechanics. The one that tells us, in the clearest possible terms, that at least one of these theories is wrong. NASA is deeply involved in this search. The James Webb Space Telescope is observing the earliest galaxies and the distribution of matter. The Nancy Grace Roman Space Telescope will map dark matter through weak gravitational lensing. The Euclid mission, with NASA participation, is doing the same. These missions will tell us more about where dark matter is and how it behaves. But they will not tell us what it is. That will require a breakthrough, a direct detection, or a theoretical revolution. This is the classical picture of a black hole, as described by general relativity. It was worked out in the 1960s and 1970s, in the golden age of black hole theory, by physicists like Roger Penrose, John Wheeler, and Stephen Hawking. The mathematics is elegant, rigorous, and as far as it goes, correct. The laws of quantum mechanics are unitary. This is a technical term with profound implications. Unitarity means that the evolution of a quantum system is deterministic and reversible, at least in principle. If you know the complete quantum state of a system at one moment, you can calculate its state at any future moment. And, crucially, you can run the calculation backward. The information about the initial state is always preserved in the final state. It may be scrambled beyond any practical hope of recovery, mixed, dispersed, entangled, hidden in correlations between particles. But it is not erased. It cannot be erased. Information in quantum mechanics is conserved. For decades, this was considered a paradox but not a crisis. The information was assumed to be hidden inside the black hole, inaccessible but not destroyed. Perhaps it was encoded on the singularity, or in the structure of space-time inside the horizon. The question was considered philosophical, unobservable, and therefore not urgent information. in the physics sense, is not knowledge. It is the specific microscopic arrangement of particles, positions, velocities, spins, quantum states. This information distinguishes one state from another. A star is different from a cloud of hydrogen with the same total mass because the particles are arranged differently. Quantum mechanics says this information cannot be destroyed. It can be scrambled beyond any practical hope of recovery, but it cannot be erased. And this is the crisis. Hawking radiation is thermal. It is random. It carries no information about what fell into the black hole. If a black hole forms, consumes matter, and then evaporates entirely into random thermal radiation, the information about the matter that fell in has been, for all practical purposes, destroyed. It has been converted into heat and radiated away. The final state, a puff of radiation, is the same regardless of what the black hole originally contained. This violates unitarity. It violates a core principle of quantum mechanics. Two different initial states, a star and an encyclopedia, say could evolve into exactly the same final state, a thermal bath of Hawking radiation with a particular temperature and total energy. Quantum mechanics says this cannot happen. The laws of physics cannot lose track of which state they started from. In 2012, 4 physicists at UC Santa Barbara, Ahmed Almheiri, Donald Marolf, Joseph Polchinski, and James Sully, sharpened the paradox further. They proved that if information is preserved, the event horizon cannot be the smooth, empty vacuum that general relativity predicts. Instead, it must be a seething wall of ultra-high energy particles, a firewall. Anything crossing the horizon would be incinerated instantly. This creates a trilemma. Either information is destroyed, breaking quantum mechanics, or the event horizon is a firewall, breaking general relativity, or both theories are incomplete, and the resolution requires something deeper than either. No option is comfortable. The black hole information paradox is not an academic puzzle. It is a crack in the foundation of physics itself. Hawking himself initially accepted the radical implication that information is destroyed in black holes. This would mean that quantum mechanics, as usually formulated, is wrong, or at least incomplete. It would require a modification of quantum theory to accommodate the loss of information in gravitational collapse. Hawking bet John Preskill, a physicist at Caltech, that information was lost. He later conceded the bet, admitting that information is preserved, and gave Preskill a baseball encyclopedia, a reference to the thought experiment about encyclopedias falling into black holes. But he never fully explained how the information gets out. The holographic principle, developed by Gerard 't Hooft and Leonard Susskind in the 1990s, suggests that all the information about what falls into a black hole is somehow encoded on its event horizon, not in the interior volume, but on the surface, like a holographic plate. This idea emerged from string theory, and in particular from the AD-SCFT correspondence, a mathematical duality discovered by Juan Maldacena in 1997, which demonstrates an exact equivalence between a theory of gravity in a higher dimensional space and a quantum field theory, without gravity living on the boundary of that space. In this correspondence, a black hole in the bulk corresponds to a thermal state in the boundary theory. And since the boundary theory is unitary, since information is manifestly conserved, the gravitational theory must also be unitary. It is a proof of principle, but it does not explain the detailed mechanism. More recently, a remarkable development has provided a precise mathematical formula for how information escapes a black hole. In 2019 and 2020, Jeffrey Penington, Don Page, Ahmed Al-Mahiri, and others developed the Island formula, a prescription for calculating the entropy of Hawking radiation over time. The key insight involves quantum extremal surfaces and entanglement islands, regions inside the black hole that are, from a quantum information perspective, actually part of the outside. After the page time, roughly halfway through the black hole's lifetime, the Hawking radiation begins to carry information. The radiation is no longer purely thermal. It contains subtle correlations that encode the quantum state of the material that fell in. Hawking initially accepted the radical implication that information is destroyed. This would mean quantum mechanics is wrong. He bet John Preskill of Caltech that information was lost. He later conceded, admitting that information is preserved, and gave Preskill a baseball encyclopedia. But he never fully explained how the information gets out. Meanwhile, other approaches to quantum gravity offer alternative resolutions. Loop quantum gravity suggests that spacetime itself is quantized at the Planck scale, made of discrete, indivisible units. In this picture, the singularity at the center of a black hole is replaced by a region of extremely high but finite density. As a black hole evaporates, it may transition into a white hole, the time reverse of a black hole, from which matter and energy can only escape. The information that fell in would be released, scrambled but intact, in a final burst of energy, possibly as a fast radio burst or something entirely new. These competing resolutions, holography, islands, loop quantum gravity, and others, represent the bleeding edge of theoretical physics. They are the territory where our current understanding runs out and the next paradigm has not yet been discovered. They are signs that we are, in some deep sense, still at the beginning. This is a beautiful and profound result. But it is not a complete resolution. The island formula has been verified in simplified models. Black holes in anti-de Sitter space, unlike our universe with its positive cosmological constant. Extending these results to realistic black holes remains an open problem. And even within the models, the detailed mechanism is not fully understood. How exactly is the information about a collapsing star encoded in Hawking radiation? The mathematics says it is preserved, but no one can give you a step-by-step description of how the reconstruction would work. The information is there, in correlations between radiation quanta, but it is deeply scrambled, irrecoverable in practice, even if preserved in principle. But these images, as stunning as they are, do not show us what lies beyond the event horizon. They cannot. The event horizon is, by definition, a one-way surface. We can see its silhouette. We can map the magnetic fields threading the surrounding plasma. We can observe relativistic jets launched from the poles, beams of plasma accelerated to near light speed that stretch for thousands of light years. We can detect gravitational waves from black hole mergers using LIGO and Virgo, which have catalogued dozens of such events. We can probe the ringdown, the brief period after a merger when the newly formed black hole settles into its final state, emitting gravitational radiation that encodes information about its mass and spin. But the paradox is not just an academic exercise. It is a crack in the foundation of physics. It tells us that general relativity and quantum mechanics, both confirmed by decades of experimental tests, are incompatible at the deepest level. One of them, or both, must be modified, and the modification will require a revolution. NASA operates telescopes that observe black holes. The Event Horizon Telescope, a global network of radio observatories synchronized by atomic clocks, gave us the first direct image of a black hole's shadow in April 2019. The supermassive black hole at the center of galaxy M87, 55 million light-years away. A dark central shadow surrounded by a bright ring of radio emission from hot plasma swirling in the accretion disk. In May 2022, it gave us an image of Sagittarius A, the black hole at the center of our own galaxy. These are triumphs of engineering and collaboration. But they do not show us what lies beyond the event horizon. They cannot. The interior, where our theories break down, remains hidden. They are places where our understanding stops, walls we have not yet climbed, questions that, when asked honestly and directly, elicit the most humbling answer in all of science. Are we alone in the universe? The wow signal whispered that maybe we are not. The fast radio bursts, with their strange periodicities and their origins in places they should not be, whisper something similar. Something that could be natural, could be artificial, and we have no way to tell the difference. Oumuamua, with its impossible shape and its unexplained acceleration, reminded us that the universe can deliver objects to our doorstep that we cannot comfortably categorize. The question of whether we are alone, perhaps the most profound question a conscious species can ask, remains completely, utterly, and humblingly open. What happens to information that falls into a black hole? The paradox tells us that our two deepest theories of reality are incompatible. General relativity says information is lost. Quantum mechanics says it cannot be lost. One of these theories is wrong. The resolution, whenever it comes, will transform our understanding of space, time, matter, and information in ways we cannot yet anticipate. It may reveal that space-time is not fundamental, that the universe is a hologram, that information is the basic substance of reality, or something no physicist has yet imagined. We do not know. And here is the strange and beautiful thing. Every NASA mission that sets out to solve a mystery ends up discovering new ones. The Curiosity rover was sent to determine whether Mars was ever habitable. It answered that question. Yes, Gale crater was once a lake, with all the ingredients necessary for life. But it also found methane spikes that may or may not be real, and organic molecules that may or may not be biological, raising more questions than it answered. The James Webb Space Telescope was built to see the first galaxies. It has seen them, and they are brighter and more massive than they should be, forcing cosmologists to reconsider their models. The Event Horizon Telescope was designed to image a black hole's shadow. It succeeded and reminded us that the interior of a black hole is a place where our theories break down and we have no idea what lies within. This is not failure. This is the rhythm of science. Every answer opens new questions. Every discovery reveals new depths of ignorance. The physicist John Archibald Wheeler wrote, "We live on an island surrounded by a sea of ignorance. As our island of knowledge grows, so does the shore of our ignorance." NASA's island has grown enormously, but the shoreline, where solid ground gives way to dark water, has grown even faster. Perhaps that is the real secret. Not that NASA is hiding something from us, but that the universe is. The universe guards its secrets jealously. It gives us hints, a 72-second radio signal, a cigar-shaped visitor from the stars, a seasonal whiff of methane, a shadow where light cannot escape, and then it pulls back. That is where the mystery lives. And that is where NASA lives too, not in the press releases or the budget hearings, but in the quiet hours when data streams in from a spacecraft billions of miles away, and someone sees something that should not be there. And for just a moment, the entire universe feels larger and stranger than it did the moment before. Because in the space between what we know and what we do not, there is room for wonder, room for the possibility that tomorrow or next year or a century from now, some astronomer will see something that changes everything. Something that makes the WOW signal look ordinary. Something that reveals what lies beneath the dark matter. What happens inside the black hole, what stirs in the soil of Mars. And on that day, whenever it comes, we will realize that NASA was not hiding anything. It was simply waiting, like the rest of us, like every human being who has ever looked up at the night sky and felt the chill of the infinite, waiting for the universe to speak again. The physicist John Archibald Wheeler, the man who coined the term black hole, who mentored Richard Feynman and Hugh Everett, once wrote, "We live on an island surrounded by a sea of ignorance. As our island of knowledge grows, so does the shore of our ignorance." NASA's island has grown enormously. The island now contains knowledge that would have seemed miraculous to previous generations, images of the cosmic microwave background, maps of exoplanets, samples of asteroids, the sound of gravitational waves, the shadow of a black hole. But the shoreline, the boundary where solid ground gives way to the dark and unknown water, has grown even faster. The shore is longer now, and the water is deeper, and the things that swim in it are stranger than anything we had imagined. That shoreline is where we find the WOW signal. It is where we find oumuamua. It is where we find dark matter and fast radio bursts and unexplained methane on a planet we thought we understood. And if you listen carefully, if you strip away the press release language and the institutional caution, you can hear, in the voices of the scientists who study these phenomena, something that sounds like awe, not fear, not frustration. Awe. Awe that we have catalogued over 5,000 fast radio bursts and cannot explain a single one with certainty. Awe that we have spent $100 million on xene detectors buried under mountains and still cannot find the particle that makes up 27% of reality. Awe that a 72-second signal from 1977 remains the best candidate for extraterrestrial intelligence in the history of radio astronomy, and we may never know what it was. That the largest organic molecules ever found on another planet are sitting inside a rover we cannot bring home. That the Event Horizon Telescope, a planet-spanning network of radio dishes synchronized by atomic clocks, can image the shadow of a black hole 55 million light-years away, but cannot show us what lies behind it. That the James Webb Space Telescope, the most powerful observatory ever launched, has found galaxies in the early universe that are too bright, too massive, too evolved to exist under current models, and cosmologists do not know why. That the Event Horizon Telescope, a network of radio dishes spanning the entire planet, synchronized by atomic clocks, can image the shadow of a black hole 55 million light-years away, but cannot tell us what lies inside it. That the James Webb Space Telescope, the most powerful observatory ever launched, has found galaxies in the early universe that are too bright, too massive, too evolved to exist, and cosmologists do not know why. At the possibility, remote, improbable, but not impossible, that some of these mysteries may have answers that change everything. Not fear, not frustration. Are we at the sheer scale of what we do not know? Are we at the possibility that some of these mysteries may have answers that change everything, answers that rewrite the textbooks, answers that force us to reconsider what the universe is and what our place in it might be? Every mystery we have explored tonight, the WOW signal, the fast radio bursts, oumuamua, the methane on Mars, the dark matter, the black hole paradox, shares a common thread. Each represents a place where our understanding stops, a wall we have not yet climbed, a question that, when asked honestly, elicits the most humbling answer in science: we do not know. And yet, this is not cause for despair, it is cause for wonder. The universe is not a problem to be solved. It is a mystery to be experienced, a mystery that deepens the more we learn, that rewards our attention not with closure, but with ever more astonishing questions. NASA was never hiding anything from us. NASA was simply doing what all of us must do, standing at the shoreline, looking out at the dark water, and waiting, with patience, with instruments, with hope, for the universe to speak again. And what we can piece together is incomplete. There are gaps in our understanding wide enough to drive a galaxy through. We do not know what most of the universe is made of. We do not know if we are alone. We do not know what happens at the center of a black hole. We do not know what sent oumuamua through our solar system or what produced the WOW signal in 1977. But we are asking. We are building telescopes and rovers and detectors. We are sending missions to planets and moons and asteroids. We are listening with ever greater sensitivity for signals from the deep. We are pushing the boundaries of theory, developing mathematical tools that would have seemed like magic to previous generations. That is where the mystery lives. In the strange moments, in the data points that refuse to lie down on the graph. And that is where NASA lives too. Not in the press releases or the budget hearings, but in the quiet hours, when data streams in from a spacecraft billions of miles away, and someone sees something that should not be there, and for just a moment, the entire universe feels larger and stranger and more mysterious than it did the moment before. And on that day, we will realize that NASA was not hiding anything. It was simply waiting, like the rest of us, for the universe to speak again. NASA's island has grown enormously in the decades since its founding. The island now contains knowledge that would have seemed miraculous to previous generations. Images of the cosmic microwave background, maps of exoplanets, samples of asteroids, the sound of gravitational waves, the shadow of a black hole. But the shoreline, the boundary where solid ground gives way to the dark and unknown water, has grown even faster. The shore is longer now, and the water is deeper, and the things that swim in it are stranger than anything we had imagined. And what we have been able to piece together so far is incomplete and provisional. There are gaps in our understanding wide enough to drive entire galaxies through. There are questions we have been asking for decades, for centuries, that remain unanswered. We do not know what most of the universe is made of. We do not know if we are alone. We do not know what happens at the center of a black hole. We do not know what sent oumuamua hurtling through our solar system. We do not know what produced the WOW signal on that August night in 1977. But we are asking. That in the end is the thing that matters most. We are building telescopes and rovers and detectors and arrays. We are sending missions to planets and moons and asteroids and comets. We are listening with ever greater sensitivity for signals from the deep. We are pushing the boundaries of theory, developing mathematical tools that would have seemed like magic to the scientists of previous generations. We are walking the shoreline, mapping its contours, wading into the water where we can, even knowing that the sea is vast and dark and full of things we cannot yet name. That feeling, the vertigo of the unknown, the dizzying awareness of how much we do not understand, is not something to be resolved or eliminated. It is not a problem to be solved. It is in the deepest sense the whole point. The universe is not a puzzle with a solution. It is a mystery to be experienced. A mystery that deepens the more we learn. A mystery that rewards our attention, not with closure, but with ever more astonishing questions. And the most important thing NASA has ever done, more important than any single discovery, any single image, any single mission, is the simple, radical, persistent act of showing us how much we do not know, of revealing the shoreline, of pointing to the dark water and saying, look at what is still out there. Look at what we have not yet understood. Look at how much remains to be discovered. And on that day, whenever it comes, we will understand something that tonight we cannot even imagine. We will look back at this era, the era of questions without answers, of mysteries unresolved, of signals unexplained, and we will see it for what it was. Not a time of ignorance, but a time of anticipation. A time when the universe was still whispering to us, and we were still learning how to listen. NASA was never hiding anything from us. NASA was simply waiting, like the rest of us, like all of us, like every human being who has ever looked up at the night sky and felt the chill of the infinite, waiting for the universe to speak again.